another RDO hangout. Today, Eoghan Glynn will be speaking about Ceilometer. We just passed the midway point in the Juno cycle, and there was a meetup in Paris to discuss progress, as well as what still needs to be done. So Eoghan's going to be talking about what's coming in Juno and what progress has already been made. And here we go.
Cool. Thank you, Rich, for that introduction. So, as Rich said, my name is Eoghan Glynn. I'm the program technical lead for the telemetry program within OpenStack, and the principal project within that is Ceilometer, and that's probably the one that you're most familiar with. So I'm the incoming PTL for Ceilometer for the Juno release cycle. So I'm going to speak a bit in general about what our top-level themes are for Juno, what we're attempting to do. Some of the goals that we have are part of a kind of a multi-cycle program, and I'll speak to that in detail and give you an impression as to where we are in terms of progress. I'll talk a little bit about how we've tried to change some of the upstream culture. So certain processes we've taken on board, some of these have grown up organically within the team, and some of them have been more in the nature of following best practices that are being seeded throughout the community after being established initially in other projects in OpenStack. And I'm thinking in particular about the Nova project, which has acted as a little bit of a trailblazer as far as process improvements have been concerned. And the pattern has tended to be that that new practices are kind of tried out for the first time by Nova, and then gradually they're kind of refined and spread out and propagated throughout the OpenStack community. And I'll talk about what changes we've made there. And lastly, I'll go through some detailed work items. So this will be at or about the level of granularity of individual blueprints or kind of tightly related groups of blueprints, and give you an impression as to what you should expect in the final Juno release, what kind of mid-cycle adjustments we've made, and basically how our priorities are evolving as we go through the Juno cycle. So as I'm going through this, feel free to pop questions that you may have on the RDO-Hangout IRC channel. But just be aware that the actual video stream or the audio stream that you're hearing is lagging real time by up to a couple of minutes. So take that into account when popping up questions and when to expect an actual response from me. Okay, so what are our top-level themes for Juno? Well, the first thing to notice is that basically it's always healthy, I think, in the life cycle of a project to have kind of a checkpoint or a health check as to how the project is doing. And as luck may have it, we had a natural point for which such a health check was applied, and that was in the shape of the recent technical committee gap analyses. Now, these analyses have been applied to each of the already integrated projects in OpenStack. And the idea is here that the bar in terms of what it takes to become an integrated project has been steadily rising. There's been this kind of grade inflation going on. So Heat and Ceilometer were the first two projects to join the traditional core projects as integrated, and that happened at the outset of the Havana release cycle. Now, as time has progressed, more projects have appeared in the scene. We've had quite an explosion of activity around the OpenStack ecosystem, and the requirements that are expected of these projects has steadily increased, and I think that's a good and healthy thing. But as far as being fair is concerned, it doesn't make sense for the projects that happen to have graduated first to have gotten an easier ride, as it were. So, in the interest of being balanced, the technical committee has basically decided to apply a retrospective gap analysis to each of the already integrated projects, and to basically determine how they would do if the decision was to be made now, whether to allow them to graduate or not. And I think this is a good and healthy thing, and it's been applied to many projects Ceilometer, heat, horizon, glance, and so on, neutron as well. And in each case, a number of concerns have been identified by the technical committee, and the ball has been kind of bounced back into the projects court to address those concerns. So that's probably our number one theme for Juno, to basically ensure all of those concerns are addressed, and that progress is seen to be made on those gaps, and that progress is kind of front-loaded within the Juno cycle. So the next kind of overarching theme is around basically grasping the nettle in terms of architectural deficiencies in Ceilometer that have been kind of hampering us from the get-go. So basically, we'll talk about how certain decisions that were made earlier on in the project's lifecycle have turned out to have had unanticipated costs down the line, and how we're looking at changing things so as basically to pay down that kind of architectural debt. I'll also speak to some new processes that we've adopted in terms of how we do our work upstream. All good and healthy stuff, and most of this is kind of informed by changes that have been seeded across the OpenStack community, usually things that have originated from the Nova project. And lastly, a bit of a stretch goal. And this is basically an ongoing objective that I've kind of set myself. And this is kind of happening in parallel with the main thrust of our upstream work. And this is to figure out the relationship between Ceilometer and a number of related projects that are going on to do with monitoring and metering OpenStack. That are approaching it in slightly different ways, and that have different groups of people involved, but are basically ploughing a very similar furrow. And personally, I have a kind of a big tent approach to these things, and I would like to see the teams that are contributing to projects like Manaska and StackTac to become more involved in Ceilometer, and for Ceilometer to learn the lessons that have been garnered by those folks in running their monitoring infrastructure at large scale in their public clouds, and to basically have the projects kind of move closer together, to share areas of common concern, and hopefully to slowly converge on a common thing. So that's something that's been happening in parallel. For those of you who are unaware of the background of Manaska, this is largely an initiative that's come from HP. It was a project I think was originally known as Yamon and went through a couple of naming cycles, and the latest is Manaska. It's largely implemented in Java. It uses Kafka as its messaging layer as opposed to Oslo messaging over Rabbit or Cupid. It uses a metrics-oriented database called Vertica, and an open source alternative to that, they've just added a driver for InfluxDB. And it's got several areas of commonality with Ceilometer. It's got a thresholding engine that does similar things to Ceilometer alarming. And it's got some kind of new stuff as well that's interesting. For example, it's got an anomaly detection module that's basically responsible for applying kind of advanced statistical techniques around forecasting and prediction bands to detect anomalies in a way, anomalies in statistical trends, that is, in a way that couldn't be done in terms of simple comparison against a static threshold, which is the way Ceilometer alarming works, or AWS CloudWatch, for example. They're both based on flat static threshold comparison. So Manaska has a lot of interesting pieces. It's a lot of points of difference, but I think we can certainly learn from those folks. And we've had a kind of, since the summit in Atlanta, we've had an ongoing conversation with them, and we're kind of learning more and more about what Manaska actually is and what it can potentially offer to Ceilometer, and how certain pieces of it could be maybe taken into the telemetry program. It's not something that we've worked out in great detail yet, but I think it is going to be something that will definitely be on our roadmap for the K cycle. So I'd just like to give folks in the community a heads up that something along those lines is coming down the pike. And lastly, StackTac, it is probably familiar to a lot of people. This is a events-based monitoring framework, and that's in wide use within Rackspace. And it takes a slightly different viewpoint to Ceilometer. Instead of being kind of metrics and samples oriented, it's more oriented around persisting events. and then reasoning over the expected sequences of events and how related events can be bracketed together to represent common workflows, such as migrating an instance or resizing an instance or something of that ilk. So, while there's lots of points of differences there between what Monasca does and what StackDAC does and what Ceilometer does, there's also points of commonality. And, we would like to leverage that commonality where possible. So I'm going to keep that kind of conversation up in the background, in parallel. And I think it's something that may well come to fruition in the time frame of the K cycle. Okay, so drilling down in more detail into some of these themes that I identified earlier. So firstly, these technical committee mandated requirements. So basically, we went through this gap analysis exercise with the technical committee, and I was just at about the time that I took over as PTL of Ceilometer. So it was kind of good timing because it gave us an opportunity to really kind of prioritize our efforts around covering these gaps for the first and the second milestones within the Juno cycle. So I guess the first thing, the most pressing concern initially to the technical committee was the lack of a explicit project mission statement. So over time, I guess Ceilometer has been there's been a persistent kind of fuzziness around its identity. And to the extent that, the most common question I have to field day to day at one point was, is Ceilometer a metering infrastructure? Is it purely about billing? Is it also going to, kind of stray into the area of monitoring and alarming? Where are the boundaries of the project? So something that was a little bit fuzzy. We wanted to keep our mandate as open-ended as possible. So we want basically to be the project that's concerned with all things to do with measurement. So basically, we did some collaborative wordsmithing, and the way the technical committee works now is that things like mission statements and resolutions and other governance-related issues are all discussed in public on Gerrit, just like a code patch would be. So basically, I submitted a patch to the government's repo setting out a proposed mission statement for Ceilometer, and we brought it through the release cycle in the usual way, and came up with an agreement with the technical committee in the end as to what Ceilometer actually is. And I think this is really useful, even though it's only 4 lines of text. It actually represented quite a lot of discussion and compromise and negotiation and collaboration to get to that point. And I think we've come up with something that everybody's happy with, that it basically gives us the scope to innovate and to move forward in the directions we want to move forward, but yet describes what Ceilometer is all about in a fairly crisp way. So basically the agreed mission statement in the end was to reliably collect measurements of the utilization of physical and virtual resources comprising deployed clouds, to persist these data for subsequent retrieval and analysis, and trigger actions when defined criteria are met. So the triggering of actions there would refer to the Ceilometer alarming feature, which basically is what's used to drive auto-scaling in heat. So for example, if you want to use auto-scaling, you basically set high and low watermarks in your heat template for your auto-scaling group, which describe basically points at which you want to trigger the addition of extra instances to handle increased load, or conversely, the shrinking down of your auto-scaling group where load is lower than some threshold. Ceilometer alarming is basically the mechanism that currently drives that. The persistent aspect refers to our metering store. So as things currently stand in Ceilometer v2, we've got storage drivers for MongoDB, which is probably our primary and canonical storage driver. And certainly it's the storage driver that's recommended for production use by most OpenStack distributions. So for example, RDO or RHEL OSP from Red Hat, or the Mirantis OpenStack distribution, to name just a few examples, they all would recommend MongoDB as the storage driver of choice. But we also have several others, including HBase, DB2, and SQL Alchemy, that can be used alongside MySQL or Postgres. And I'll talk to that in a little bit more detail in just one moment. And lastly, there's the element of the mission statement that applies to both physical and virtual resources. So I think this is quite significant because it basically gives us the freedom to meter usage data around user-visible cloud resources, such as instances, volumes, images, that kind of thing, but also gives us the freedom to go after more hardware-oriented metrics, such as the metrics that we're currently collecting using SNMP. So we can get host-level metrics on, say, CPU load averages for an entire compute node, as well as the individual CPU utilizations for the instances that Nova has scheduled to that compute node. Another example would be IPMI sensor data. So one of the things we're working on in Juno is the capability to consume notifications from Ironic, and those notifications will contain sensor data from IPMI, so things like temperatures, fan speeds, voltages, that kind of thing. And these are, quite hardware-oriented metrics. So we run the entire gamut from the very fabric or infrastructure-oriented metrics up to cloud resource-related things that relate more to the user view of cloud resources. Okay, so that's our mission statement. The next big kind of point was our SQL Alchemy driver. So why is this important, you may ask, if, as I just pointed out, it's actually the MongoDB driver that's recommended for production use by most realistic distributions of OpenStack? Well, the thing is, there's always been a slight licensing question around Mongo. And the thing is that Mongo itself is AGPL licensed, which is fine. But the client library, pymongo, that Ceilometer uses to communicate with the backend database, that's Apache licensed. And MongoDB Inc. have been very, very clear all along that they don't intend the AGPL-ness of MongoDB itself to virally infect the client driver. That's not their intention, and they'll provide you with a legalistic document to that effect if you so desire. But it's still always been this kind of lingering, well, for people who are not so happy with the MongoDB licensing, there needs to be an alternative. And this principle has been applied to all OpenStack projects that use Mongo. So the other one that comes to mind would be Marconi, whose their primary driver is based on Mongo also. So basically, one of the requirements that the technical committee has set our project is to basically also support a SQL Alchemy driver. And that's not intended to support large-scale production, but it is intended to be runnable in small deployments, in proofs of concept and so on, and also for it to be possible to use it in the gate. That's the continuous integration testing gate that's used upstream to verify every single patch that's proposed for review and to re-verify it again before it's actually merged to trunk. Now, the reason why SQL Alchemy is used in the gate for integration tests that involve Ceilometer is because up to very recently, the gate was very, very Ubuntu oriented, and in particular, it was oriented towards the previous LTS version of Ubuntu, which was 12.04 or Ubuntu Precise. So basically, the version of Mongo that was available on Precise was relatively old. The version of Mongo that Ceilometer needs is newer because we use some of the newer primitives that have only been supported for Mongo up to Mongo 2.4. So basically, because of this version mismatch, we were forced to enable Tempest tests that use Ceilometer in the gate to use the SQL Alchemy storage driver instead of our preference, which would be MongoDB. Now, the issue here was that that relational databases just aren't very well suited to storing metric data. I mean, this is just a fact of life. It's nothing specific to what Ceilometer does. It's just the nature of metric data is that it's not very well suited to being efficiently stored and queried from relational databases. So our original SQL Alchemy driver, to be honest, did not exhibit very positive performance characteristics. In fact, it wasn't really usable, even at the scale of the gate. So a major concern that we needed to address, and as a matter of urgency, and we have done so, was to improve the performance of SQL Alchemy such that it was possible to run it successfully in the gate, and also to stand over it as a realistic choice for small scale deployments, particularly proofs of concept on a single physical host or over a small number of physical nodes, and we've done that. So related to that was our coverage in the Tempest test suite. So Tempest basically is the testing harness that's used upstream to test integration tests. So most projects in OpenStack are tested at multiple different levels. They're tested first off internally via a set of unit tests, right? There is also a phase of upgrade testing that basically I'll speak to in a moment. And finally there's the Tempest tests, which are a set of what you'd classically call integration tests. They're run against a dev stack, or indeed Tempest itself can even be pointed at any cloud installation, even a public cloud. And basically what they do generally is run through various API scenarios and ensure that the expected behavior actually occurs when run against a set of interacting services. So you would spin up Nova, you would spin up Cinder, you would then spin up Glance, and then you would, for example, have a test that does something like start up an instance that that's based on an image that's retrieved from Glance and has attached to it a volume of block storage provided by Cinder. So you've got multiple services all interacting with each other, and that level of integration is what's being asserted by the Tempest tests. Now, one of the requirements on integrated projects is that they do have this level of Tempest test coverage. The problem with Ceilometer, though, was that, well, we had a bunch of patches proposed in the time frame of the previous cycle and in the time frame of Icehouse. A lot of these patches couldn't land because of the performance issues in the SQL Alchemy driver. So having addressed those performance issues, we've now unblocked a bunch of those Tempest tests, and our Tempest coverage is looking a lot better even at this stage within the Juno cycle than it was previously. But we still have a few little kind of speed bumps, as always. So one thing that we're currently figuring out is the complications caused by the advent of what we call branchless Tempest. So previously, Tempest was just like any of the other service projects. It had a master branch, which related to development work that was ongoing for the current cycle, but it also had branches for stable branches that were basically referring to previous versions. So, for example, during the Juno cycle, or during the Icehouse cycle, for example, there would have been a parallel branch maintained of Tempest, and that would be used to do the continuous integration on the stable Havana branch. And previously to that, there would have been stable Grizzly, and all the ways back in time. Now, the thing is that this was problematic from the point of view of the QA team, and they wanted to move away from maintaining these stable branches within Tempest and instead move to what they call branchless Tempest, where there is only one Tempest, and instead tests are selectively skipped or enabled depending on what's actually being tested. And when branchless Tempest was first being mooted, there was a bunch of scenarios kind of war-gamed out around, well, what would happen if some new feature was added, or the version of the API was bumped, or whatever? How could we have the same tests basically running against master and also running against the stable version or the stable branch for the previous release? Now, some of those potential issues were basically addressed, but not everything. So there's some scenarios basically that Ceilometer is currently struggling with, whereby we're testing behaviors that are not directly mediated via API-driven interactions, where instead we expect, for example, a notification to be emitted by a service such as, say, Cinder, and that notification to be picked up by Ceilometer in certain circumstances, and as a result, metering data to show up in the Ceilometer metering store. And that kind of testing that a side effect has occurred is bit more complicated when it comes to branchless Tempest, because branchless Tempest really is predicated on the idea that the existence of a feature is externally discoverable, that it's possible to kind of go to the API and figure out what the current set of capabilities are, such that you can know which tests to enable and which to skip. So we got a live thread on the mailing list currently on that. We've discussed it at length. For example, we discussed it yesterday at the PTL's meeting. So it's kind of a live issue that we're currently grappling with, and no doubt we'll bring that to a solution. But even up to now, even accepting those complications that are caused by branchless tempest, we have greatly increased our tempest coverage over the Juno cycle, which is a very good and positive, healthy thing. Okay, so the next big gap that was identified by the technical committee related to documentation. So while Ceilometer had fairly, fulsome developer-oriented documentation, which described things like how to set up a dev stack and enable that dev stack for Ceilometer, what meters to expect, how to add a new meter, how to add something to our pipeline.yaml configuration, all of that kind of thing. There was a little bit of a dart of user and operations-oriented documentation. So we're working on that. We're writing a new admin guide, and to some extent it's kind of repurposed from the RDO Getting Started guide for Ceilometer that I wrote a while back. And the intention is there that this will be added to the overall administration guide for OpenStack, and we'll have much more complete ops-oriented documentation as a result. And then the last kind of requirement from the TC was around the Grenade upgrade test harness. So this is kind of a neat idea. It's a simple but a useful thing. So as many of you will be aware, OpenStack has traditionally been a little bit weak around upgrades. So this weakness basically would have ranged from a lack of support for live upgrades. So it's not possible, it's never been possible, even though we're slowly moving towards the goal of the capability of doing rolling upgrades such that the services remain live during the actual upgrade. But that's been complicated by various things, such as the requirement to apply database schema migrations and so on, which usually require taking down the services for somewhat of a limited period in time while the upgrade is in motion. The other kind of weakness has been that certain failures that have been caused by upgrading a live system in the olden days, in the early days of OpenStack, only really appeared in the wild when people actually tried to do the upgrades. And obviously that wasn't a great situation to have. It wasn't a great user experience. So the Grenade testing framework is basically an attempt to smoke out these upgrade-related issues and to smoke them out early and before, well prior to anyone actually getting their hands on the software and attempting to do this in production. So what Grenade does is very simple. It basically spins up a dev stack based on the old version, which would be generally the last stable release or the latest from the stable previous branch. It starts up all the services and basically creates some resources. So, creates a few images, a few volumes of block storage, spins up a few instances. Then it shuts down all the services and basically upgrades to the latest on master, while leaving those resources running. So even though the services have been shut down and upgraded, and the database migrations applied, and then the services restarted, all the while the initial set of resources, such as the instances that were spun up, the volumes of block storage that were created, the images that were uploaded to Glance, those things continue to exist. And one of the assertions that Grenade makes is the ability to check that those resources has survived the upgrade. So basically, as far as Ceilometer is concerned, our participation in Grenade involves adding Ceilometer to the set of services that are installed and shut down and upgraded and restarted in that way, and also to make assertions around Ceilometer's view of those surviving resources. So where we'd have, for example, a Nova instance that was spun up in the old cloud and survived into the upgraded cloud, we want to, for example, make queries relating to some metrics that have been gathered for those instances by Ceilometer, and ensure, for example, a query where the duration of the actual query, the time span that we're interested in, spans the old through the downtime and into the new, and ensure that that the metrics that have been gathered in each case are kind of compatible and they look the same, and that queries that span that upgrade time period are valid and are treated properly. So we've made a lot of progress on these TC mandated requirements. We did a review just after the Juno 1 milestone went out, And the TCU is pretty happy with our progress so far, and they're holding us to having all of this stuff closed off by Juno 2. So this will have, kind of accounted, I think, for a lot of our energy over the Juno cycle. But by the same token, it's all been healthy stuff, largely around things like paying down technical debt, things that would have had to be done eventually anyway. So it's really great to get all of these things out of the way, and basically to start from a point where we can kind of hold our heads high and say that we've met the requirements, the higher level of requirements that are currently applied to newly integrating projects. Okay, so that's kind of related to technical debt, but we've also got this kind of lingering architectural debt. So what I mean when I speak about this is basically decisions from an architectural point of view in Ceilometer that were made kind of in the really early part of the life cycle of the project, which have turned out to be problematic, right? So basically the main one here that we're addressing currently is this notion of snapshotting resource metadata for each data point basically in our metering store. So when Ceilometer collects data, what it does is say CPU utilization for an instance. It's recording a sequence of numbers that represents currently the CPU utilization for that particular instance is 42. And in a minute's time, it might be 44. And then in another 10 minutes, it might be 39. So these are basically just a sequence of numbers, which in and of themselves are fairly lightweight things. But in addition to that, we also store a snapshot of the resource metadata alongside each of those data points. And that would include things like the image UUID that was used when this instance was booted up, or the flavor of that instance. Is it an extra large instance, or a tiny instance, or a medium instance, that kind of thing. Now, much of that resource metadata, while not immutable, is actually quite static in practice. It's infrequently changing. Now, the reason why Ceilometer actually changes these snapshots or stores these snapshots of resource metadata is to make it easy to reconstruct the timeline of resource state. But as it happens, that timeline can be reconstructed in a much kind of simpler and more lightweight way by simply looking at the events that were emitted, the notifications at each of the major transition points or phase changes in the life cycle of the resource. So if you were to look at the metadata associated with, for example, an instance in Nova, you'll find that most of the fields that Ceilometer currently stores are very static. And the things that are capable of changing, such as we say the instance, the current state of the VM, that only changes at very well-defined points that tend to happen quite infrequently. So the state of a VM might change when you go through a suspend resume cycle, or the flavor of the instance might change when you do an instance resize or an instance migration. So these are things that happen fairly infrequently, or not at all, indeed, during the life cycle of a typical resource, a typical instance. So it'd be much more efficient to just store the actual events that reflect those phase changes, rather than to snapshot the resource metadata for each data point. So basically, what we want to do is avoid these kind of inefficiencies in space and time when it comes to actually writing this fairly heavyweight representation of the resource for each data point, and also the resulting inefficiencies at query time. So the idea is basically to reimagine Ceilometer as more like a time series data as a service. So this is kind of a multi-cycle effort that we've kicked off in Juno, and what we would expect is the output or part of the Juno release to have a kind of a technical preview of this work, and basically for the full story to be available at the end of the K cycle, where we have full support for things like migration of pre-existing data and all that kind of thing. So it's currently been prototyped in a project that's been spun up by Julien Donjou, who's my predecessor as PTL of Ceilometer, and it's called Gnocchi, after the Italian food. So that's there's a bit of an Italian food theme going through the naming on that project. And basically the idea here is to store sample data in a fairly lightweight way as time series, where it's shorn of the resource metadata. Instead, the resource metadata is stored separately in a resource indexer. And basically there's a lot of control around things like granularity, pre-aggregation, roll-up, and the data retention policies. So still relatively early days there. We spent a lot of our time in Paris at our mid-cycle meetup last week and discussing the Nokia API, and in particular how the semantics of the Nokia API, and which the intention is will form the kernel of the upcoming v3 API in Ceilometer, that how basically those semantics can be mapped onto, in addition to a canonical driver that Julien is working on based on the Pandas analytics library in Python and Swift as the storage backend, basically how they can map to that canonical driver, and also how they can map to a variety of other metrics-oriented databases. So I've written a kind of a straw man alternative storage driver for Nokia for InfluxDB, which is an interesting metrics-oriented database that basically I referred to earlier in relation to what Manaska use. And it's got a lot of capabilities for storing time series and then reasoning over those time series and doing interesting types of aggregations. And we actually had the prime developer for InfluxDB at our mid-cycle, so we got the kind of the inside track on how a lot of the internals of InfluxDB are organized, and how we need to shape the Nokia API to make best use of the mechanisms within Influx for doing things like downsampling on demand and expiry, to implement the Nokia data retention policies. So I think that was very productive, and I think we've a much clearer view of where Nokia is going and basically what is needed in the API to make it efficiently implementable over multiple different storage drivers. And the intention is over time, just like in Ceilometer, we'll have a variety of different storage drivers for our time series as a data service component. So initially we may have, for example, Pandas plus Swift as one option, InfluxDB as a second option, and then going forward over time, one could imagine, for example, OpenTSDB based driver, a Cassandra based driver, and so on. So that's all interesting. It's something that I'm giving a heads up on now, even though this is not something that'll be available to run in production at the end of Juno. But it's, as I said, it's a multi-cycle effort, and it's the direction that we want to go in. So, hence the reason why we want to kind of make it known at this early stage, and get feedback and input and so on. So that's our architectural debt. Some changes to how we do things upstream. So basically, one thing we've done is we've kind of changed to a very collaborative kind of decision-making process, and this was, I suppose, one thing that we did in advance of the summit in Atlanta. So, for example, the scheduling of the Ceilometer Design Summit track, the decision as to which proposals were accepted and which amalgamated and which rejected, that was all done and in a collaborative way across the entire core team, as opposed to being kind of presented by the PTL as a fait accompli. So, I think that's a good way to work, and I see a few other projects adopting that same model. For example, we used a Google Doc to kind of vote on, as kind of a spreadsheet in Google Docs to kind of vote on the proposals that each individual core member was interested in seeing and how they wanted things to be merged and all of that. And I see some other projects did similar things. For example, OOO used an Etherpad to do the same thing. So it's a practice that's been adopted by other projects as well. Another good, healthy thing that we've done, even though it adds a bit of overhead, is the adoption of a specs repo. So this was a practice that was trailblazed by the Nova team, and it was intended to avoid this scenario whereby a lot of projects were getting a lot of what you might call drive-by blueprints. So anybody could rock on up to Launchpad, write a blueprint, and submit it. And there was generally like a large backlog of untriaged blueprints that were kind of clogging things up. So and then the approval of those blueprints was often kind of a rubber stamping affair without sufficient detailed oversight. So the whole idea behind the specs repo is that instead of doing that, the first point of contact is actually to propose a detailed spec. And this specification covers issues like, well, what is the problem we're trying to solve here? What are the alternative solutions? And this is, really useful to capture, especially for things that are, controversial, where there's a division of community or division of opinion within the community as to which way we should go. And then issues like, well, what's the impact on documentation? What's the impact on deployers and packagers? What changes are required to the client library? What Tempest test coverage would be required? And to force basically all of these issues to be considered upfront, a priori, well in advance, rather than putting some of those issues in the long finger, like, oh, we'll figure it out when we get there, we'll cross that bridge when we get there. And that has tended to be problematic in the past. So Ceilometer specs is basically a place where things can be reviewed on Garrett as if they were code, even though there are kind of free text descriptions of approaches to solving various problems. And then Launchpad blueprints from now on will really just be a placeholder for a link into the specs repo. Another good process that we're adopting is around feature freeze proposal. So for Juno 3, rather than going down to the wire as we've done in the third milestone in previous release cycles, what we'll expect is for the initial patches to be proposed at the latest 2 weeks in advance of the final deadline. So this is to avoid the issue that we've had, and I've actually been one of the worst offenders in this myself, is where basically people underestimate the amount of time that it takes to shepherd patches through the Garrett review pipeline. So people end up proposing fairly chunky patches with non-trivial features, perhaps even series of related patches, very close to the deadline, and then require basically a feature freeze exception because the feature hasn't landed by the time the milestone is cut, because they haven't really accounted, the coding work has been done, but they haven't really accounted for the process of bringing those patches through the whole review work cycle, and the number of trips to the well, and responding to comments and feedback, and implementing that feedback, and pushing a new version of the patch set, and so on. So the whole idea behind FPF is to ensure that there's sufficient time for that to occur, so that the patches really are landed and bedded down well in advance of the final milestone being cut, so that we don't have feature-oriented work bleeding into our traditional stabilization period. And that's the period between the third milestone of a release cycle and the final release. So it's generally like a 4 to 6 week period, and that's intended to be around fixing release critical bugs and not around landing features that should have been landed earlier in the cycle. Okay, the next thing that's kind of on the list there is the mid-cycle meetup. So the first time we've done this in Ceilometer was the week just past. We went to an event in Paris, hosted by Icehouse. And in fact, it was a Ceilometer meetup, but also there was representation from a bunch of other projects. There were people there from Ironic, from Oslo Messaging, and from a bunch of other projects, and from OOO. And basically, it really was a very productive 3 days. It was the Ceilometer team were kind of in conclave for most of the 3 days, discussing things mainly around the time series data as a service initiative that I talked about. But there was an awful lot of cross-fertilization between projects going on as well. I think the whole mid-cycle idea is it's a very healthy development, and more projects are adopting this. So again, it was probably Nova was the first a couple of cycles ago, but now most projects have some form of meetup, and I think it's really good, because at Summit itself there can be a little bit of over exuberance, whereas at the mid-cycle it's much more realistic. So folks are halfway through the cycle, they're aware that the window is closing, and it's really down to brass tacks, and it's really a good way of concentrating the mind. And that kind of face time halfway through the cycle, I think, is really useful and valuable thing. So we did that last week, and I think it was definitely a productive exercise. Okay, other things, we've had more direct engagement with the QA team, and so we want to basically have a situation whereby we're feeding requirements directly to them, and we're hearing their feedback, and slowly we start speaking the same language. And I think we're well along the way to getting there. And also, one thing I've tried to do is basically to be more proactive around the kind of the blueprint to resource matchmaking. So by resources, I mean actual developers with bandwidth available to contribute time and attention to bringing features over the line, and to basically to have that kind of ongoing to be continually kind of maybe moving things around as prioritizations change or as people's individual circumstances change. So, you know, we'll see at the end of Juno cycle how successful that was, but that's definitely been one of the objectives that I've set myself. Okay, so some of the detailed work items, I've actually spoken in detail about a fair amount of these already, so I'd probably go through these quite quickly. So obviously the time series data as a service work, or the Noki project, that's a multi-cycle thing. So there's a canonical implementation up on Stack Forge that uses Pandas and Swift. I've written a strawman, not fully functional storage driver for Influx, just as a kind of proof of concept, and it was largely intended to kind of frame discussion at the mid-cycle and to smoke out certain kind of potential impedances between the Noki model and the way Influx, the degrees of freedom provided by Influx. And, you know, the idea is basically that over time, we'll integrate this with the metrics pipeline in Ceilometer, so you can configurably publish data to Noki instead of to the classic metering store. And we'll also integrate it, obviously, with the alarm evaluation pipeline, because that's currently hits the Ceilometer API service. And that requires certain things like the ability to look at metrics in a dimensional fashion. So by dimensional in that context, I mean the ability to slice and dice metrics in various different ways and not just aggregate by resource. So for example, to have an overarching view of a certain metric, we'll say CPU utilization, aggregated over an entire autoscaling group. So clearly that'll require some mapping of the semantics that are currently used to the semantics offered by Noki. So that's all interesting work that's on our plate going forward. We have an intern from the OpenStack outreach program for women, a woman called Eoghan, who's basically working on an aspect of this that basically will support period spanning statistics. So this is something we've not supported traditionally in Ceilometer. The ability to have aggregates, such as averages and medians, those type of things, what I mean when I say aggregates. There's a class of aggregate functions that basically require that results are fed from one period to the subsequent period. So these would be things like moving averages and various exponential smoothing algorithms. So traditionally what we've done is that our aggregation is involved taking all of the data points for an individual period and ring fencing these off as a standalone piece. So period spanning will basically allow us to free ourselves of that restriction so that we can add to our stable of supported aggregates this class of functions that basically span individual periods. So there's that. Then there's the SQL alchemy viability, as I mentioned. So we've actually made a whole ton of progress on this, and we brought it from being unviable to being a quite viable state that's basically now running happily in the gate and is suitable for use in small deployments and in proofs of concept. And the way we've done that has involved doing things like removing our long deprecated version 1 API. So that allowed us to make a lot of simplifications in the database schema. Elements of the schema that were purely there to support the ways in or the viewpoint of the version 1 API, which had been deprecated for a couple of release cycles. So we'd given everybody fair warning that it was going away. So we finally removed it and had all of the knock-on simplification of our database schema as a result, which actually gave a very discernible boost in performance. We've further rationalized that schema. We've gone through a kind of a renormalization followed by a selective denormalization process. We've also greatly simplified the kind of upsert logic. So there was logic in the SQL alchemy driver code that basically involved, attempting to do an insert and then retrying on failure. And the way that was doing it tended to lead to kind of storms of rollbacks and retries where you had concurrency on the scene. For example, you had multiple Ceilometer collector agents that were each trying to step on each other's toes, as it were. And that kind of interaction is now greatly cleaned up and much more efficient. In this process, we've been fortunate in the sense that the author of the SQL Alchemy ORM library, a guy called Mike Baer, has joined the OpenStack community and basically has been in a position to give us a lot of detailed feedback and input, and that's all been very valuable and insightful. So some other detailed work items. Things things that that basically we're working on. So over Icehouse, we added support for SNMP polling, and one thing we noticed was that SNMP offers a whole bunch of different metrics, and each one is identified by an OID, which is just a dotted decimal kind of number. And basically, in our first kind of iteration at this for Icehouse, we had support for a bunch of different OIDs, different metrics that we thought people would be interested in. But as it turns out, you can't really predict, exactly what folks are going to be interested in. And some people are have an interest in different metrics that we didn't envisage originally. And then we kind of got to thinking, well, do we really want to require that we write new Python code every time a new metric needs to be gathered for SNMP? So we came up with this idea of declarative posters. So a poster in Ceilometer terminology is simply a piece of Python code that's responsible for acquiring data, grabbing data from some API. So this might be a public RESTful API that's exposed by a service, or it might be the local hypervisor, or it might be an SNMP daemon. So basically, declarative posters, this is a notion whereby via configuration, the polling logic is declaratively set out, and it can be changed the same way as you can change configuration, rather than requiring new Python code is written every time you want to gather a new metric. So that's one good thing. Another good thing is the large-scale reduction in the degree of chattiness with the SNMP daemon. So previously, we were issuing a separate SNMP command for each of the individual metrics that we wanted to retrieve, whereas in fact, SNMP 2C and greater versions basically allows commands to be issued in bulk, which is a much more efficient way of doing it. So that work is ongoing, and that's targeted at Juno 2 currently. Our central agent, so this has basically been another long-standing architectural issue in Ceilometer. So it's a single point of failure in the sense that there's no way of horizontally scaling the central agent in active-active mode. You can scale it out in active-passive mode and gain some reliability that way, but there's no load sharing between individual central agent instances. So what we want to do is get to a point where the workload can be partitioned across multiple horizontally scaled out central agents. And the way we've been looking at this is to use a StackForge library called TOS, or TOOS, I'm not quite sure how to pronounce it, which is basically like a facade over distributed coordination protocols like Zookeeper. And basically this will allow coordination between individual central agents, for example, master-slave patterns that's based on an election for master, and then the actual workflow allocation. We're still figuring out the details of how to do this, but one proposal that's on the table is to use the task flow library. So the task flow is a mechanism that's used in Glance and Cinder and several other places that allows work to be kind of described as a task, and then there's tasks to be posted to a task board, and that task board then to be polled by a pool of workers that are available to basically grab the tasks as they appear. So that's been worked on for the central agent, and in the meantime, we've also got a partitioned alarm evaluator. Now, this is something I did for Havana, so this is going back a couple of cycles, and basically I kind of reinvented a distributed coordination protocol for it that was based on fan-out RPC. So clearly we don't want to be reinventing the bicycle continually. So what we want to do is rebase that coordination protocol between the partitioned alarm evaluators. So these are components that are responsible for doing threshold evaluation for some subset of the currently enabled alarms, and basically having those scaled out evaluators coordinate with each other such that each alarm is being evaluated by one and only one evaluator at any moment in time. And again, similar kind of considerations for that. The idea is to use TOS for that coordination, and potentially to use TaskFlow for the actual alarm assignment. So that's currently been worked on. Actually, there's a patch for that up in Garrett for an amount of time, and the author of that patch, Cyril, was at the mid-cycle meetup last week, and with some detailed discussions as to what changes are needed to that to get it landed finally. Okay, and then the next item is this events completion. So basically, up to now, or up to, I suppose, Icehouse, Ceilometer has been largely oriented towards data points, as in what we call samples. But there's also the stack view of the world, which is to view things in terms of persisting individual events. So an event is generally a AMQP notification that's emitted when some kind of phase shift is gone through by one of the resources in your cloud. So, you know, an instance is started up, an instance is resized, an instance is paused, an instance is terminated, that kind of thing. And basically, the OpenStack services follow a pattern of emitting these notifications. And what we've done previously is we've taken these notifications and distilled them down to individual data points. Now, what we want to do also is have the capability to selectively store these events themselves, because reasoning over the sequence of events after the fact actually gives a very useful view as to what's happened over time. You can kind of reconstruct this resource state timeline. Now, in the Icehouse cycle, the StackTack folks largely contributed a events persistence tier and an events API, but it was implemented only for the SQL Alchemy storage driver. So what we want to do is basically have that kind of feature parity spread out to the other storage drivers. So we've already got it landed for HBase, and there's a patch up currently under review that's close to being in a condition that'll be possible to land it and to provide the same functionality for MongoDB. So this is kind of important because as we move towards these more lightweight time series oriented storage ideas, we will want to be able to rely on the events storage mechanism or the events persistent mechanism to give us that kind of resource state timeline. Okay, so some other detailed work items, many of which I've actually spoken to already in this Hangout, so I'll just go through this quite quickly. So the QA side, we're beefing up our Tempest and Grenade coverage. I've spoken to that. And we have the complication around branches templates that we're currently grappling with. But you know, we'll get there, we'll figure it out. We've got the IPMI sensor data, this is quite interesting. So we agreed with the Ironic folks at Summit that basically they would own the polling cycles. So the reason here is that in order to be able to call into the IPMI interface, there is a credentialing requirement. There's a username and password that needs to be known, and that username and password is currently stored by Ironic. And we don't want this leaking out into the Ceilometer configuration. Also, there's a requirement to kind of protect IPMI against over-aggressive polling. So we don't want Ceilometer to drive the polling directly, in which case, you know, it might be possible to actually configure Ceilometer such that it locks up IPMI by just calling into it at too frequent a cadence. So basically, the way we're approaching this is for Ironic itself to actually do the polling, for it to control the cadence, and for it to continue to own the credentials. And then for it to also do filtering such that it takes this raw sensor data and then it basically emits notifications over AMQP for those pieces of sensor data that might be interesting to actually record as metrics. So these would be data that have a numerical orientation and that are inherently varying, as opposed to, you know, data that are quite static. So that's an interesting feature. And from a Ceilometer point of view, what we'll be doing is basically consuming these notifications that are coming from Ironic and you know, persisting these data as Ceilometer meters. So that work is ongoing currently. We've got the blueprints landed for both Ceilometer and Ironic, and the implementation work is progressing on both sides. Lastly, a few kind of miscellaneous things that are interesting that I thought I'd mention. One is the metering of network servicing, so our network networking services. So we've got, for example, load balancing as a service metering that's already landed for Juno 1, and then for Juno 2, we've got firewall as a service and also VPN as a service. So here we want to, for example, be capable of metering, you know, how many open connections there are currently, how many existing VIPs there are, what the state of those VIPs are, and so on. Another interesting one that we're currently discussing is the ability to write a transformer in Ceilometer that does arithmetic combinations of samples from multiple meters. So we have this pattern in Ceilometer currently whereby we have transformers that are capable of deriving sample values from other samples. So for example, our CPU utilization metric is derived from a primary metric, which is effectively cumulative CPU time. So what the arithmetic transformer is about is extending this capability. So via configuration, you can say, okay, I want to combine samples from meter 1 and meter 2. I want to apply this rule to the two values and produce meter tree as a result. So a typical example might be, say you had a meter which was memory.total, and you had another meter which was memory.used, and you wanted to express that as a memory.utilization percentage. So you wanted to, take these two values, apply a very simple arithmetic rule, and produce a new derived meter from samples that cross multiple meters. That's actually quite an interesting and useful feature that's currently being worked upon. And then one last thing that I thought I'd throw in there, which is basically another thing that's kind of under active consideration, and this is very relevant to the mid-cycle we just had in Paris last week. And one of the hot areas of discussion was around how to dig ourselves out of the eventlet hole. So eventlet is used right across the board in OpenStack. And it's got, it's basically, it's got certain strengths, but it's also got some glaring weaknesses. And one of those is that it relies a bit too much on black magic happening behind the scenes. In particular, it relies on a kind of cooperative multiprocessing model that's driven by monkey patching. So if you're using eventlet, you have to effectively monkey patch the standard libraries so that, for example, if you're doing some potentially blocking I/O, that the thread doing the I/O will know to cooperatively yield at certain points in time, so that the the eventlet kind of green threads model can actually work. So that's a lot of stuff kind of happening behind the scenes, underneath the hood, quite kind of obscure as to what's actually going on. And when things go wrong, for example, when we see timeouts in test runs that are related to eventlet usage, it can be quite hard to diagnose and quite hard to get to the bottom of what's going on. So in Python 3, there's the concept of async I/O, and there's a backport of many of the concepts that async I/O brings to the table for Python 2.x, and obviously OpenStack is based on Python 2.7 and 2.6 as things currently stand, and that backport of the async I/O principles is called Trolleus, and one of the main author of that, a guy called Victor Stine, basically was at mid-cycle. And basically, he's got the idea around switching or deprecating eventlet and slowly switching over to this async I/O usage model, and to do so in kind of baby steps, in a graduated way, to pick a particular project and to start replacing various aspects of its use of RPC dispatch and timer tasks and all of the other elements of asynchrony that we rely on eventlet for, to start switching over basically to using Trolleus. And that'll be a kind of a multi-cycle effort. And one of the proposals that's on the table is that at Ceilometer, because it's got a fairly wide and interesting use of RPC as things currently stand, to basically have that as the first beneficiary of this effort. So that's something that's still under active consideration. There's a fairly hot thread on the developer, on the mailing list, the upstream dev list currently, where people are discussing that. So it's not clear as to whether this will actually occur and whether it'll occur in the time frame of Juno. But if it does so, I think it'll be a healthy thing. And it's definitely something to keep your eye open for, because basically, certainly for us, near the code face in OpenStack, it offers some very definite potential benefits in the medium term. Okay, so I'm just at about the top of the hour, so just gone over by 3 minutes. So hopefully that gave you a detailed and complete insider's view of what's been going on in Juno, and what we're actually spending our time doing, and what our prioritization is, and how that prioritization has kind of evolved over the cycle so far. So I haven't seen any projects or any questions on IRC as yet. Okay, I see Rich as prompting for questions. So I'm probably, when you're hearing this, it's kind of lagging, as I said earlier, a little behind reality, a little behind real time. So I'll give it a minute or two to see if any questions pop up before we call it a day.
All right, well, there seem to be no questions, so thank you very much, Owen. And for those of you that are watching this after the fact, please feel free to ask follow-up questions on the RDO IRC channel on Freenode or on the OpenStack-Ceilometer channel on Freenode. Another great place to ask questions is ask.openstack.org. Once again, this is Rich Bowen with the RDO project from Red Hat. Thanks for watching.
Cool. See you, folks.